What's up, everybody? It's Dan from SageMathTutoring.com. And here is a review sheet for a student. This student has a test on Friday. It's going to be the opposite of fun. And this has to do with, it's like Algebra 2 stuff. All right, let's take a look at the directions. Graph each function, state the domain and range of the function. Well, stating the domain and range is going to be relatively easy once we graph it first. I'm actually thinking that before I even dive into any of these, let's get very clear about some of the parent functions. For example, the parent function of the absolute value of x looks something like that, okay? Where there's a vertex at 0, 0, and the slope of this line is up 1 over 1, up 1 over 1, also known as 1 over 1. And the slope of this line will be down 1 over 1, down 1 over 1, also known as negative 1 over 1, also known as negative 1. So in other words, it's a kind of a perfect V, where it's like perfectly slanted. Now, obviously, there's all kinds of transformations that you can apply to that, but we're not going to worry about that right now. Another parent function worth remembering is most definitely, well, clearly there's linear equations, which are interesting, but one particular kind of linear equation is something like that, where that would be literally a horizontal line, okay, cutting through 5. Similarly, if we had something like x equals 1, which, by the way, these are not really parent functions, but that's okay. We want to get clear about what vertical lines look like. That's a vertical line. When it says y equals 5, that's a horizontal line, so that's important to understand. Let's see. And this would be an x value of 1. Definitely, we should know about the parent function of a parabola, which looks like that, with that vertex at 0, 0. What else should we know? There's all kinds of stuff we should know. So let's see. Make that a little bigger. We should also know that the square root function looks something like that. And we should also know that anytime you have this sort of rational situation, that looks like this, where there's an asymptote vertically here and a horizontal one here. And this kind of gets closer and closer to that vertical blue asymptote there, but it's a rough draft sketch. So these are examples of the parent functions. In my opinion, really good idea to understand these. You could also maybe throw in the linear equation, which perhaps the parent function, I think, would actually just be that. And that would just be a slanted line like this. A lot of students are used to there being a different slope other than 1, and also maybe a y-intercept here. But the parent function would be something like that. It's this perfect line that's like that. Okay, so those are some parent functions. We're going to take a look at this, though. We'll leave that parent function stuff off to the side. So we have an absolute value function here. We also have a horizontal line over here. There's a piecewise function. Clearly, there's some action happening at the x value of 2. Looks like the teacher, as far as I could tell, is sort of a fan of tables. So we're going to go with that approach. And what I'm gathering from the teacher, because there are different ways of doing this, what I'm gathering from the teacher is the teacher wants you to be clear that, okay, well, this function is true for all the x values less than 2. So let's actually start with 2 and just find out what the x value would be. And she is putting this open circle next to that x value of 2 to communicate that the x coordinate of 2 actually isn't really here. There's going to be an open circle there, okay? But it's still nonetheless a good idea to find out what the y coordinate is that corresponds with that. So that's something that we could do and find out the y coordinate, which we're going to do soon. Another thing we could do is recognize that this function is true for all x values less than 2. So it's not the worst idea in the world to maybe investigate the x value of 0, and it's not the worst idea in the world to investigate the x value of -2 either. Now, when x is 2, we've got 2 times the x absolute value of 2, which is 4. 4 minus 4 is 0. That right there is going to be 0. And when we plug in 0, it would be 2 times 0, which is 0, minus 4, that's going to be negative 4. And then over here, when we plug in negative 2 in the absolute values would produce a positive 2. So that would be 2 times positive 2 minus 4, which would be 0. So the points, let's see, negative 2 comma 0 exists on the graph, negative 2 comma 0. The point 0 comma negative 4 exists on this graph, which is right there. And there's a hole right there at 2 comma 0. So that would be right there. So this absolute value function looks like that. And with regards to this one right here, it's vital to recognize that this is literally just like y equals 5. That's a horizontal line. I had mentioned what horizontal lines look like before. I called it y equals 5 over here. Actually, it's the same thing. So yeah, that's going to be a horizontal line at the y value of 5 for all x's greater than or equal to 2. So that's going to be 1, 2, 3, 4, 5. That's going to be like right there, and that's a closed circle. Is that 5 spaces? 1, 2, 3, 4, 5. Yes, it looks like it is. And then it's going to go to the right. Okay. In my opinion, we don't really need a table for that, but you could make a table if you want. It would just be y equals 5. It would be 5, 5, 5 on that column. With regards to problem number 2, well, over here, oh, we want the domain and range. My bad. So the domain of number 1 is all the x values from negative infinity all the way up to here. Now, there's a hole here, but there is an x value represented here, so it actually keeps going. So the domain would be negative infinity to positive infinity. Infinity symbols always get the parentheses next to it. The range would take into account the lowest point, which is this, that's negative 4. So it goes from negative 4 all the way up. Hopefully that makes sense. So that would be a range of negative 4 included, which is why it gets brackets, and then it goes all the way up. All right. I actually think I do not have time, unfortunately, to do the evens. I'm going to do just the odds. So for my student at home, unfortunately, too much on my plate, not able to do the whole thing, but I'll do the odds. All right, so hopefully that's going to be helpful. I will say a few words about this. That's a square root function, so that's going to be a square root function shifted over to the right too. This is a parabola that's kind of flattened, where the vertex is down here at -1. It's kind of flattened like that. So that's what I can say about that. With this one, we are looking at -4/3 times the absolute value. So this is an absolute value function horizontally shifted to the right one, and also it goes vertically shifted up 4. Another way of seeing it is that this is sort of the vertex form. It kind of looks like the vertex form of like a parabola, but it's absolute value. And the vertex is going to be at 1, 4. Okay. So if you want the vertex when you're dealing with absolute value like this, just know that the x coordinate of the vertex is going to be the number right here, only it's going to be the opposite sign. So it's going to be +1, and the y coordinate of the vertex is going to be this number here, okay? So that's the vertex, 1, 4. I'm going to write that right now, 1, 4. That's 1, 1, 2, 3, 4, right there. It's also -4/3. Now, there's a couple ways to do this. One way is to use a table. I'm actually just we're gonna stick with the table because I have a feeling that's what the teacher wants, okay? Now, when you're doing a table with something that has a vertex, you might want to put the vertex in the middle. Now, we already discussed what that vertex is. It is 1, 4. Then, before you worry about y at all, just get a couple values to the left of 1 and get a couple values to the right of 1. Now, a couple values to the left of 1, clearly 0 would be good. -1 would be pretty good. Then we have 2 and 3. Now, you might be wondering, why am I doing that? Well, because this absolute value thing V shape is symmetric. So if I just find these y values, they're going to be matched over here. So let's use 0 because 0 is very good to work with. 0 plugged in would give me a -1, absolute value of -1, which is +1. +1 times -4/3 is -4/3. -4/3 plus 4. Let's think about it. -4/3 plus 4 is really -4/3 plus 12/3, which is 8/3. Okay. So that's that. When we plug in -1, it would be -1 minus 1 in there, which would be -2. Absolute value of -2 is +2. +2 times -4/3 is -8/3. -8/3 plus 12/3 is 4/3. Now, as I said before, that will be matched over here. This is going to reflect and become an 8/3 here, and this one is going to reflect and become a 4/3 here. Now, these are annoying to graph, okay? 8/3 is like 2 point something, okay? 2 point something. So that's going to be here-ish. And then we got this 4/3, well, that's really 1 point something. So that would be right there. And we could match it on the other side. And most teachers would be sort of fine with 5 points. Okay. Now there is another way I could have done this that I like a little better than this, but once again, I think the teacher wants something like that. I'm not going to do number 4, but I am going to discuss it. With regards to this one, first of all, the parent function for that is something along these lines, right? I already discussed it. Of course, we have a 2 and it's negative. So since it's negative, it's going to be this flipped upside down, all right? This is a parabola right here, flipped upside down as well, so the horns point downward. To find the vertex, you'd have to use -b/2a to find the axis of symmetry. This is a parabola that's written in standard form. So you're going to want to find that axis of symmetry, and then plug it back in to get the y-coordinate of the vertex. Worst comes to worst, you could, well, here's one thing you could do. You could use the axis of symmetry. I want to discuss this a little bit. I know I'm all over the place, but I want to just provide as much value as I can in the short amount of time that I have. So the truth is that this could be represented as something that looks like this. And this is in the standard form of a parabola. Okay, now I'm insisting on writing a 0 here because it's a placeholder for this C. Now, hopefully my student at home recognizes that the axis of symmetry is -b/2a. The a in this case is -1, as you can see right here. The b in this case is 4, as you can see right here. So the axis of symmetry would be -4/2 times -1, which is going to just be 2. Now, what you can do with that information is actually going to be really good. What you can do is you can set up a table. You can recognize that, okay, fine, the axis of symmetry is at 2, so that's going to be the middle x term. And then you go to the left from there. It would be 1 and then 0 and then 3 and then 4. And then you just find out maybe these y terms, okay, and then they're going to be reflected over here. You could also find the y-coordinate of the vertex, okay? But anyway, the point is that if it's written in standard form, you can use this to find the axis of symmetry. That's x = 2. I would strongly recommend putting that x value in the middle here. Find a couple x values above, a couple x values below. That will get you your 5 points, and then you can graph it from there in a way that your teacher will appreciate. This graph, although this graph only applies for all x's greater than 0, so there would actually be a hole associated there. So you could plot a hole at that point. You're still going to want to find that y value, but you're going to plot an open circle at that point, okay? Hopefully that makes sense. Once again, I am going to have to move along. Okay, so with regards to this shenanigans, we're going to do the odds. We're going to do 5, 7, and 9. So first of all, they're asking for the domain at the end of the day. They want us to just evaluate or find these functions. So f plus g of x, that's very straightforward. For most students, when you're adding, that's probably the easiest of these kinds of problems. It's literally going to be f of x plus g of x. And we have like terms here and here, so they would get combined. It would then become 3x squared, looks like plus 14x, and then minus 24. So that is f plus g of x, but they do want the domain. Now the domain for a parabola, this is a parabola, the domain is all real numbers, also known as negative infinity to positive infinity. Okay, so that's important to recognize because a parabola looks like this, and it certainly goes up forever. But if the leading coefficient's positive, then the horns point up. If that was a negative, the horns would point down. So it goes up forever, but it also goes out forever. It goes out forever. So that means all these x values will be captured by the graph, we could say. So that is that one. Hopefully that makes sense. Looking at problem number 7. I would say that this one's trickier than it looks. Obviously, it is subtraction, no question about that. But when you subtract this stuff, you're going to have to be careful with distributing the negative. So it starts with g, so it's going to be 3x minus 4 minus the quantity of 3x squared plus 11x minus 20. And distributing the negative, we would have to do 3x minus 4 minus 3x squared minus 11x plus 20. The like terms are, here are the x terms, here are the constants. So I'm going to write that as negative 3x squared minus 8x plus 16. Now that is a parabola with the horns pointing down, something along those lines. Looks like there is that y-intercept of 16. Now this is standard form. When it's written in standard form, the constant does not give you the y-coordinate of the vertex. The constant gives you the y-intercept. The vertex could be higher than that. In fact, I think it is in this case, okay? So the domain here is also negative infinity to positive infinity because there's no real restrictions here. All right, so that's problem number 7. Problem number 9. Let's see. I will say a few words about the even ones, but we're just not going to do them. So it's going to be f over g for problem number 9. F over g of x. Well, that's going to be f of x, which is this, over g of x, which is this. And the f of x, hopefully you are in the habit of asking yourself, can that be factored? Well, the answer is yes, that could be factored into this, okay? Now, if you have to pause the video and work that out on your own, that's fine, but this is true, okay? Now, this would cancel, okay? Now, we are kind of going through the motions, but we're already going to recognize that, the bottom line is x cannot be. X cannot be. We already know this. It can't be 4 over 3, because if it was 4 over 3, then this would be a 0 down here, right? Now, in case you're wondering, how the heck did you know that? Well, what you could have done is you could have set 3x minus 4 equal to 0, and you could have solved for x, and then you would have quickly realized that, x equals 4 over 3, which means that if x was 4 over 3, then this would be 0, and that means that x is not allowed to be 4 over 3, okay? So at the end of the day, x is not allowed to be 4 over 3 because it would cause this whole thing to be undefined. So you're going to want to make that mental note. That's a very important mental note to make, all right? Now, when it comes to canceling, though, we end up canceling, and then we have our f of g of x equals x plus 5 after that cancellation. So what that means is this really is sort of a linear equation that's like this, except at 4 over 3 there's a hole. That's what's happening, okay, in this. It's a linear equation after the cancellation, but we also know that x is not allowed to be 4 over 3 because it used to have a denominator of 3x minus 4. So there's a hole there, and what that means is that the domain is going to be negative infinity all the way up to that 4 over 3, and union symbol is a decent way to go. And then it's going to be 4 over 3 not included all the way up to positive infinity. Notice how there's parentheses next to the infinity symbols. Notice how there's parentheses next to the 4 over 3 because 4 over 3 is not included. Okay, now with regards to which number to put first, you always put the lesser number on the left. I'll say it again. Every time you have these parentheses, there's going to be two numbers, and you always put the lesser number on the left. So there's literally nothing lesser than negative infinity. So that means that if negative infinity is part of it, then that's always going to go on the left. There's nothing greater than positive infinity. So if positive infinity is part of the situation, then that positive infinity is always going to go on the right. Here it is. Okay. So hopefully that's helpful. So that is that one. Talking about the other ones, though. Problem number 7, or problem number 6, you would have to do the same thing where there'd be a distribution, okay? It would be this minus that, and that would once again result in all real numbers being in the domain, because that would be a parabola. This would be multiplication. Due to the 3x squared times 3x, when you multiply these things together, that's going to become 9x cubed. So that is a cubic function, and the leading coefficient would be positive, which means the end behavior is going to be like that. Okay, the end behavior is going to be like that, and there's no restrictions on the domain. So therefore, we would be, let's see, having all real numbers, okay? Now, in case you're not clear about how to multiply a trinomial times a binomial, imagine this is your trinomial and you're multiplying it times a binomial. I like to actually go from here. I multiply this times everything, and then I multiply this times everything, and then you just combine like terms. With regards to this, it's going to be very similar to this one, except g is going to go on top. It's going to result in a scenario where you're going to reduce, and it's going to be 1 over x plus 5. And that is such that you have to be careful because we're going to discuss that. I have to discuss that one. So for that one, it's going to be g over f, so that's going to be 3x minus 4 over, we already kind of did this as 3x minus 4 over x plus 5, so let's just get that factorization part over with. Hopefully you can see immediately x is not allowed to be 4 over 3. And x is not allowed to be negative 5 in that case. So that's two restrictions on the domain, okay? So that means that x could be anything except those two numbers, okay? And even after we cancel these, leaving us with just a 1 on the top, even after that, it would be still the case that x is not allowed to be these two numbers, okay? So the domain in that case would be, looks like it would be negative infinity all the way up to negative 5, but then it would be from negative 5 all the way up to 4 over 3, but not including 4 over 3, and then it would be 4 over 3 all the way up to positive infinity. So hopefully that makes sense. Okay, that's 3 sections of the domain. Okay. Focusing on the odd ones, let's see. Okay, so we already have a square root function, which is annoying. We're gonna deal with that when we get there. With regards to these, this is a special kind of problem. Notice how this says g of f of x, where there's a letter f of x in there, or there's x in there. Now we have numbers in there. When it comes to having numbers in here as opposed to x, you're gonna wanna go from the inside out. Now, what I mean by that is you find out what g of 1 is first separately. You go off to the side and you ask yourself, what's g of 1? Well, that's going to be the same thing as g of x, except it's going to be a 1 instead of the x. So instead of 3x, it's going to be 3 times 1. And that's going to become 1/4. So g of 1 is 1/4. So what this is really asking is not what is f of g of 1. What this is really asking is what is f of 1/4. That's what it's really asking. Then you can just be like, okay, well, f of 1/4 is this thing except 1/4 instead of x. Now, that would be, this is 28 over 4, so that would be 29 over 4. And that could be split into radical 29 over radical 4. And that could be radical 29 over 2. Okay, so that's the first part. That's this one. Okay, now on to this one. What's g of 2? Well, you're going to have to find that out separately. G of 2. Or actually, pardon me, it's f of 2. Sorry. We got to find out what f of 2 is first. Right, because that's the inside part, right? Like I said, we got to go from the inside out. Let's find f of 2. So f of 2 just on its own is that which is 3. So when they ask for what's g of f of 2, what they're really asking is what's g of 3. That's what they're really asking. Well, that would be whatever this is, except 3 plugged in for x. So that's going to turn out to be 1/10. All right. So that is the answer to that one, unless I made a careless mistake, which I do not think I did. When it comes to these, it is the case that you do not go from the inside out. You ask yourself, what's on the outside? G is on the outside. So you, in a way, you're kind of going from the outside in. So what do I mean by that? Well, what I mean by that is you can essentially rewrite the whole thing only as g, right? And g is 1 over something. It's 1 over 3 times something plus 1. Now, what goes inside the parentheses, though? F of x goes inside the parentheses. F of x is radical x plus 7, according to this information. So if I was to simplify that further, I wouldn't really have to do much. I just kind of rewrite it without the parentheses. And at that point, we would have to ask ourselves, well, what value of x would cause this whole thing to be undefined, right? Because that x value cannot be in the domain. Well, one way of figuring that out is to literally take the denominator and set it equal to 0. Now, when we do that, it would become 3 radical x plus 7 equals -1. Then it would become radical x plus 7 equals -1/3. And then we could square both sides. We could square both sides to get rid of that radical symbol. And it would become x plus 7 equals 1/9. And we could subtract 7 from both sides. Now 7 is really 63 over 9. Okay, 63 over 9. So it's going to be 1/9 minus 63 over 9. Okay, and that would be -62 over 9. Okay, now here's the deal. Whenever you square both sides, you have to check for extraneous solutions. That might be an extraneous solution. How do you know if it's an extraneous solution? Well, you plug it back in. Okay, you plug it back in. Now, -62 over 9, plug back in for x. Let's make sure this is clear. The radical symbol goes there. So -62 over 9 plus 7 over 9. Well, 7 over 9 is 63 over 9. So -62 plus 7 over 9 plus 63 over 9 would be 1 over 9. That would be 1 over 9. So it would be the square root of 1 over 9. Now, the square root of 1 over 9 is 1/3, right? So that would be 3 times 1/3, which is 1, and it would be 1 plus 1. So that would not equal 0. That actually would not equal 0 because this would turn out to be positive. That's kind of one way of thinking about it. So when I plugged this back in, it did not equal 0, and that turned out to be an extraneous solution, which is actually, in a weird way, that makes our life easier. We don't even have to worry about this value. But it was worth checking. You got to set the denominator go to 0, see what happens. Now, we're not done yet. There's another restriction that basically says that this radicand, the x plus 7, the thing that's under the square root symbol, that is not allowed to be negative. It's allowed to be 0. It's allowed to be 0. It has to be greater than or equal to 0, though. Okay? Can't be less than 0. So what we're going to do here is we're actually going to force it to be greater than or equal to 0. And we're going to find out all the x values that would apply to that situation. Well, after subtracting 7 from both sides, we can very clearly see that x could be greater than or equal, it could be anything greater than or equal to -7. And that is all you need to know with regards to the domain, because this turned out to be an extraneous solution. So what I'm seeing is actually it's impossible for this to be 0, because this is always going to pump out a positive number. And it's going to be a positive number plus 1, so therefore it's always going to be a positive number down here. But it is true that you have to be careful underneath the radical. We definitely don't want this to be negative, right? You can't have a negative under the radical, so x has to be anything greater than or equal to -7. So the way to write that in your interval notation is that it goes from -7, and it should be brackets actually, all the way to infinity. So I use brackets because it could be equal to -7, so -7 is included in the domain. Okay, looking at determining algebraically if g of x is even or odd. Well, g of x is right here, and I'll write it. Now, if you want to find out if something's even or odd, you got to apply a particular test, and that test is to see what happens if you plug in -x instead of x. So it becomes 1 over 3 times -x plus 1, and let's see what happens there. We end up with -3x plus 1, and that is sort of similar to the original function, but there is this negative that's in front of the 3. Now, one thing that's worth doing is to see if you could extract that negative out. In other words, factor it out. So it'd be negative out here. Still got a 1 up there. But when you factor out a -1, you'd have to change the sign of everything that's down there. Okay, so it would become positive 3x, but it would become -1 there, right? So if you were to factor out a -1, it would become negative this, okay? Now, if it was -1 over 3x plus 1, then we'd be having an odd function, okay? But because you know it's an odd function, if after plugging in -x, you end up with negative of the original function, okay? But we have negative with 1 over 3x minus 1. So this is neither even nor odd, okay? You might be wondering, how do I know if it's even? Well, you would know if it's even if after plugging in -x, you end up with the same original function, okay? For my student at home, that should most definitely be familiar. Let's talk about 12. Similarly, you're going to start from the inside out. Find out what g of -1 is first. Let's say that turns out to be 10 for all we know. I don't know. Then it would be f of 10, and then you find out what f of 10 is. And you apply the same process here. Start from the inside, find out what f of -10 is first, and then let's say that turns out to be 7 or something. Then you're asking yourself, okay, well, what's g of 7? And then you go on that mission. In this case, it would be f of g of x, meaning it would be radical. All right, this is worth doing. I have to do this one. F of g of x, because this one's a little crazy with the domain. This would be radical. Instead of x, we're going to write empty parentheses plus 7. What goes inside the empty parentheses? Well, that would be 1 over 3x plus 1. I do not think we need to simplify that much more. So we're going to leave it like that. Now, we need to find the domain. In other words, we need to find out what is x not allowed to be, and then assume that x can be everything else. Okay? Well, first of all, we can't have an x value that would cause this to be undefined, so I think we could agree that x is not allowed to be -1/3. right? It's also the case that this radicand cannot be negative. It could be 0, but it cannot be negative. It could be greater than 0, but it cannot be negative. So what we're going to do is when it comes to the square root shenanigans, you're going to want to make it greater than or equal to 0. And then just find out, oh, what x values would correspond with this situation. So you're going to subtract 7 from both sides. That would become 1 over 3x plus 1 is greater than or equal to negative 7. At that point, well, a couple different things we could do. I'm going to multiply both sides by 3x plus 1. And that would become negative 7 times 3x plus 1. And then we would end up with 1 is greater than or equal to negative 21x minus 7. Then let's see, we could add 7 to both sides and we would get 8 over there and we'd have negative 21x. And then we could divide both sides by that negative 21. Now when you divide an inequality, both sides have an inequality by a negative, you got to flip the direction. So it's going to be x is greater than or equal to, we could say negative 8 over 21. So yeah, x has to be greater than or equal to negative 8 over 21, and x is not allowed to be negative 1/3. So that's confusing. That's pretty confusing situation. We have these restrictions right here. These are the two restrictions that we just found when trying to figure out what x is not allowed to be. Okay? So, what do you do? Well, what the teacher seems to like, because I looked at the way that she went about things, what the teacher seems to like is to map out the critical values. Now, the critical values, one of them is certainly negative 1/3. Now, negative 8 over 21, negative 7 over 21 is negative 1/3. So negative 8 over 21 is a little bit to the left of negative 1/3. We're going to make it nice and spaced out like that. That way we can see what we're working with. Now, what you can do is also recognize, well, it's definitely not negative 1/3. There's a big gaping hole there because we know for a fact that x cannot be equal to negative 1/3. But the question is, what about this section? What about this section? And what about this section? Okay, I'll even color code it. Here's the red section, here's the blue section, and here's the yellow section. We're going to investigate each one separately. And what do I mean by investigate? What I mean by that is, what you do is you can plug in any old number into the radicand. And if it gives you a negative result, then it's bad. Because this radicand is not allowed to be negative. So what we're doing is we're going to investigate x values that could cause it to be negative, and in which case we're going to not include those in the domain. Now, any x value here that causes the radicand to either be 0 or greater, then that can be included. Negative 1/3 under all circumstances not included. So we can start, we'll start over here because it's easy. If you plug 0 in, right, that would be 1/3 plus 7, and clearly that is workable because that's positive, okay? Then you could find a number that's perhaps, less than negative 8 over 21. Now remember, negative 8 over 21 is kind of close to negative 1/3. Something less than negative 8 over 21 would be something like negative 1. So you could test that, negative 1. Let's see what's going on with negative 1. Well, when you plug in negative 1, it will be 1 over negative 3 plus 2, right? So that, or negative 3 plus 1, pardon me, which would be 1 over negative 2, which is negative 1/2, and it would be negative 1/2 plus 7, okay, negative 1/2 plus 7, so that's going to be positive, and that's okay. We are happy when it's positive, okay? So if you plugged in negative 1 into the radicand, it would result in a positive situation. Now, what about the in-between values? Well, that's going to be tough because, again, negative 8 over 21 is, um, really close to negative 1/3. So it's just like, I don't know, what's a value that we could test here, to be honest? It would be a little crazy. Well, to me, this is where decimals would be helpful because negative 1/3 is really negative 0.333 repeating. And then negative 8 over 21 is really approximately negative 0.38. So something in between could be something like negative 0.35. Now, if you were to plug negative 0.35 into the x here, what you would get is ultimately a negative 13, I believe. So I'll say that again. If you plug a negative 0.35 in for x here, you're going to get a negative 13, I believe, and that would be a negative number. Okay, the bottom line is it's negative though, and you could always test that for yourself with a calculator. I would use a calculator. So that's negative, so that's bad. We don't want negatives. So in this section, all these x values are included in the domain. None of these x values are included in the domain, and all these x values are included in the domain. Now, these are called critical values, the negative 8 over 21 and the negative 1 over 3. They're called critical values. We plotted them on a number line, and we tested out the different partitions. So how would you represent that information in interval notation? Well, it goes from negative infinity all the way up to this negative 8 over 21, and negative 8 over 21 is actually included. Then we actually skip over this whole region here, right? We skip over that whole region. So we could do our little union symbol, and then we're just immediately talking about this part where it's going to be parentheses, negative 1/3 up to positive infinity. Why parentheses? Because remember that negative 1/3 is not included. So hopefully all of that makes sense. You could always pause, rewind the video, yada, yada, if you have to. So amazing. Okay, looking at the other things. Well, yeah, we already talked about that. We already talked about that. We already talked about that. Yeah, we talked about all this. Okay, so moving on. Find the inverse of each function, determine blah, 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 blah. Okay, so we're going to do 17 and 19, looking at 17. Well, first you got to find the inverse. Well, that part's relatively straightforward. All you have to do there is replace f of x with y first, just for the sake of sort of convenience. There is this restriction, which we're going to keep our eye on. In fact, we're going to think about that restriction right now. So this could be kind of interesting, actually. So this is a parabola, but there's a restriction. So the parabola, though, the original function, is a parabola that has a vertex at 3, 0. Okay, 3, 0. And under normal circumstances, it would be kind of like that, a little bit like that, maybe actually stretched upward a little bit, but it would look like that. But the thing is we're only taking into account the x values that are greater than or equal to 3, which means that we're only really taking into account the black part here, okay? That's the only part that's really actually included in this function. Now, this passes a vertical line test. It's indeed a function. Now, by the way, if you were to pass a horizontal line over it, it would pass that test as well, meaning the horizontal line would only intersect this black thing at one point at any given moment, okay? So it passes what could be considered the horizontal line test. Now, if it passes the horizontal line test, if the original function passes the horizontal line test, then it can be concluded that the inverse will pass the vertical line test. And then it can be concluded that the inverse is a function. So we already know the inverse is going to be a function. Now, before I embark on the journey of finding the inverse function, I still want to look at this graph, and I want to get a visual depiction of what we can expect soon, okay? Now, the inverse of a function will always reflect over this imaginary slanted line that has an equation of y equals x. It's this perfect slanted line. Now, if we were to reflect this black part over this slanted green line, what we would end up with is the inverse function graph. So that means the inverse function graph would be located here at 3, and it would kind of poof out like that and go like that. Okay, something along those lines. So when you focus only on the yellow one, disregard the black one, only on the yellow one, that yellow one is the inverse function, and that yellow one is clearly a function. Okay, it's clearly a function because it would pass the vertical line test. So what's going on with the inverse though? Well, we already got here. We simply rewrote the original function. Here's the original function. Here it is again, except I replaced f of x with y. Now you're going to do another move. Now the other move is to replace all the y's with x and vice versa. Okay. And in this case, you could actually replace this with a y is greater than or equal to 3, because that's actually true. Then, well, you could solve for y. That's what you do. So you could divide both sides by 2, and then you end up with this thing. And then from there, you would have to square root both sides. Now, when you square root both sides, you should be in the habit of going plus minus there. Then after that, the left would say this, and the right-hand side would say this, without that exponent of 2, because the exponent of 2 canceled with the square root symbol. At that point, you can add 3 to both sides. Now, typically what you're going to want to do is write the 3 over here with plus minus in between. Now, remember, y has to be greater than or equal to 3, so it's going to be 3 plus that. It can't be 3 minus something, okay? So it's going to be 3 plus something, all right? So, yeah, I mean, that's what you got to do. And it's going to be 3 plus a really positive number, because the square root of whatever is going to pump out either a 0 or a positive number. So we could disregard this negative here, okay? At the end of the day, the inverse function is really just going to be 3 plus that. Now, it's the case that, that's a 2. It's the case that the graph of that looks something like the yellow thing, which we already figured out before, okay? Now, what do they want? They want the domain and range of the inverse, okay? Well, the domain, you can see clearly here, it goes from 0 to infinity. And with regards to the range, well, we kind of already figured that out. This range is all y values greater than or equal to 3. So as far as the domain goes, we're looking at 0. Well, 0 is included. We're looking at 0 included to positive infinity. And then with regards to the range, it would be from 3 all the way up to infinity. Okay, so that's 17. Looking at number 19. Well, let's see. No restrictions, which is fantastic. The original function is f of x equals 2 plus radical x plus 3. I'd like to get a sense of the parent function. That is a square root function, which tends to look like this. Under normal circumstances, that would be like a parent function, but it's shifted over to the right 3, or to the left 3, I should say. So it goes 3 in that direction. And it's also shifted vertically upward too. So really, it shifted to the right, to the left, -3, and up 2. So it's really looking something like that, like this, to be honest. It's like, whoa, like that. And then, you know, XY coordinate plane. Now, I'm going to first get sort of clear on what the heck the inverse might look like. And The reality is the original function keeps going like that. So the inverse function is going to be reflected. So it's going to be like here, and it's going to go like that. Okay, so that's what it's going to look like. And in the same way that this point was -3, 2, this is going to be the same numbers, but switch. So instead of -3, 2, it's going to be 2, -3. So that's going to be 2, and that's going to be a -3 right there. I am going to advocate getting a quick rough draft idea of what the two functions are going to look like. The inverse won't necessarily be a function, but in this case it is actually. It's a function because it would pass the vertical line test. It's not like it curves in that way. It goes forever in that direction, okay? In the same way that this red one goes up forever, the blue one goes to the right forever, okay? So cool. That is going to be helpful, I think, probably. So then if you're going to find the actual inverse function, you're going to want to replace that f of x with y. And then you're going to replace all y's with x's and vice versa. And then you're going to want to solve for y. We could do so by subtracting 2 from both sides. We end up with this. We're going to square both sides. And when you square both sides, one way of representing that is to simply write x minus 2 squared, and that's going to equal this. And then you could subtract 3 from both sides, and you would get x minus 2 squared minus 3. Now, this is a parabola. However, the domain is just this part, right? It goes from, looks like it would be +2 all the way to infinity. Now, you might wonder, well, how am I supposed to communicate that? Well, you could communicate it by just mentioning the domain, or you could say something like, for all x values greater than or equal to 2. That would be a valid way of kind of describing this graph. Now, one thing I noticed that the teacher did is the teacher took the original function and found the domain and the range first. Okay, now the domain of the original function, perhaps based off of the red graph here, she immediately recognized that the domain is clearly going to be -3, -3 to infinity, and that the range is going to be from, looks like it would be 2 to infinity. 2 is included. And that when it comes to the inverse, the reverse is going to be true. Okay, when it comes to the inverse, the reverse is going to be true. So, in other words, the domain of this blue inverse in the yellow box is going to be 2, infinity, which is clearly represented here, and also you can kind of see it on the graph. And the range would be the -3 to infinity, which can be seen on the blue graph, which is the inverse graph right there. So that's that. Let's see, looking at problem number 16. That's a line, and a line is clearly a function, and if you were to reflect any line across that slanted sort of y equals x reflection inverse line thing, then the result would be another line, and all lines pass the vertical line test. So all lines are functions. Except, actually, I take it back. Vertical lines are not functions. Vertical lines are not functions. So if you end up with a vertical line, it's not going to be a function. By the way, if you started with a horizontal line and then you find the inverse of that, it's going to be a vertical line. Why? Because when you reflect this red horizontal line over the green slanty line, you're going to end up with a blue vertical line, and that blue vertical line would fail the vertical line test. So I take back what I said. But any other line is a function. So that's interesting. This one's going to be relatively easy. The domain and range should be all real numbers across the board with both the original and the inverse. When I look at 18, I'm seeing something that is probably too complicated to take like a graphing approach. First of all, there would be a vertical asymptote at -4 because if x was -4, then this would be undefined, so that tells us there's a vertical asymptote. There would also be a horizontal asymptote, just so you know, at 5/2. And the reason I know that is because the degree of the top matches the degree of the bottom. When that's the case with a rational function, you know that there's a horizontal asymptote at the fraction formed by the coefficients, 5/2. So that would be the case. And, you know, if you were to graph this, it would end up looking kind of like that. Okay, now that is going to be a nightmare trying to like reflect that across and, you know, figure that out. So this one, in my view, is a little bit too complicated to take a graphing approach. But what you can do is you can realize that when it comes to the original function, we know that x is not allowed to be -4, right? And we know also that y is not allowed to be where the horizontal asymptote is. And we already talked about where the horizontal asymptote is. It's at 5/2. Now, for my student at home, if you have to review the rules of horizontal asymptotes, then do it, okay? But I'll tell you that if the degree on the bottom is more than the degree on the top, then there's a horizontal asymptote at 0, which means that y would not be allowed to be 0 in that case. So I'll say that again. If the degree on the bottom, the exponent on the bottom is more than the exponent on the top, then the horizontal asymptote is at 0. If the exponent on the top is equal to the exponent on the bottom, the leading, you know, the degree, the highest exponent, then the horizontal asymptote is the fraction formed by the coefficients. And if the degree on the top is greater than the degree on the bottom, then there is no horizontal asymptote. Okay, and for our purposes, that's all you need to know about that. Okay. But anyway, the point is that this pertains to the domain and this pertains to the range. This is the restriction on the range. This is the restriction on the domain as it pertains to the original function. So we already know that the inverse function, due to the sort of rule of inverse functions, is that it's going to be the reverse. It's going to be the case that y is not allowed to be -4, and it's going to be the case that x is not allowed to be 5/2. So that just leaves us with one mission, which is to find the inverse function itself. Now, the original function I'm going to rewrite only with y instead of f of x. Now we're going to make the switch. Okay. And at that point, we are attempting to solve for y. We can multiply 2y plus 8 to both sides. And therefore, we would have this. And then we could, well, we could distribute that. It's looking like that's what we need to do. So this would become 2xy plus 8x equals 5y. Now at that point, you're going to want to get all the terms that have y in it on the same side and all the terms that don't have y on it on the other side. So we could subtract 5y from both sides. We'd end up with 2xy minus 5y. We could also subtract 8x from both sides, giving us that negative 8x over here. Now at that point, the whole purpose of doing that is that we could now factor out a y to get it closer to being isolated. And we would have this. And at that point, what could we do? Well, we could divide both sides by the blue parentheses, and that would leave us with y equals negative 8x all over 2x minus 5. So that would be the inverse, and these are the restrictions on the inverse, okay, which are sort of the opposite of the restrictions on the original. Now, I just looked at the teacher's answer, and what the teacher did is the teacher did a little bit differently. It's the same answer, but it just looks different because what the teacher did ultimately, well, it's not what the teacher did, but let me just prove that this answer is the same as the teacher's answer. So this negative could go down here. Why not? And you could also distribute the negative into the parentheses on the bottom. So if you were sort of intent on making sure that the numerator or even the fraction looks like it's just a positive fraction, you could go ahead and distribute that, and it would become 5 plus 2x down there. And that's the answer the teacher gave. Graph. Okay, looking at the odd numbered problems, which is just that one. How about that, huh? So, determine by composition whether each pair of functions are inverse. Well, what you could do is you could plug one function in for the x placeholder of the other, and then if you get an x as a result, then they are inverses. So let's find out what happens when we figure out what f of g of x is. Well, that would be 3 over g of x, which is that. And that would just become x after simplifying it. Now, in case that's not clear, it would be 3 divided by the fraction of 3 over x, which is really 3 times the reciprocal of 3 over x. So that's really going to be 3 times x over 3. The 3's would cancel, and that would give you an x. Same thing's going to happen vice versa. So these are inverses. So talking about the other one, you would have to do the same thing here where you have to find f of g of x. And basically, if that gives you an x after simplifying everything, it would be an inverse. You could also check g of f of x. And then if that after simplifying gives you an x as a result, then these are inverses of each other. Okay, that's how you could determine by composition. Now you could determine it in other ways. You could just literally find the inverse of this by setting that equal to y equals 3x squared minus 5, and then replacing the x's with y's and vice versa, basically doing what we just did, right? And then just checking to see if they're inverses from that point forward. And I have my reasons, but I'm seeing that this would probably not be an inverse. Maybe if it was plus minus or something, maybe that'd be an inverse. All right, 22, the table shows some values for the function f. What is the value of, it should really be a little negative 1 right there. What's the inverse function of f of negative 2 or whatever? Okay, this is actually really easy. If it was just f of negative 2, well, the answer would be 7, right? Imagine they were just asking for f of negative 2. Well, that would be 7 according to this table, because this is the original function. Whenever you see f of negative 2, that's basically them saying, when x is negative 2, what does y equal? Well, x is negative 2 here, y equals 7. So f of negative 2 equals 7. But this is the inverse function. So you got to kind of think backwards with that. So basically, when it comes to the inverse function, you're asking, when this is negative 2, what's that? So this would be 4. Okay, f inverse function of negative 2 is equal to 4. Okay, and for the record, based purely off of this information, the inverse function, 7, is negative 2. Okay, so you got to think backwards. If the normal function is such that they're asking f of negative 2, well, that means when x is negative 2, what is y? So with the inverse, it's going to be, maybe a way of seeing the inverse is if y is 7, what is x? That's a good way of saying and thinking about it. Okay, that's what's being communicated with the inverse. As it pertains to the table, if y is 7, what's x? Well, x is negative 2. Similarly, as it pertains to the table, if y is -2, what's x? Well, x would be 4. Okay, that's another way of seeing it. Looking at problem number 23. The formula for the surface area of a sphere is that. Find and interpret the inverse of that. Well, right. Okay, I'm gonna replace that with an A. Instead of A of R, I'm gonna replace with an A because it's surface area, whatever. You could replace it. You just call it A. Basically, what we want to do is just solve for R. That's ultimately what we're doing. This is code for get R by itself. Okay, and we're gonna do that. How do you do that? Well, first of all, you could divide everything by 4 pi. That would give you this R squared thing. Then you could take the square root of both sides, and that's going to be plus minus this. Yeah. So that's what that would be. Now, since we're dealing with the real world, though, R has to be positive. It would not make sense to have a negative radius. So we'll just kind of leave it here. Now, some teachers would insist that there's no radical being applied to the denominator at the final answer, but I think the teacher's probably fine with that. They ask you to interpret the inverse. So interpretation means if you're given an area, a surface area already, then you can use this inverse to find the radius. Okay. The original sort of function is helpful if they give you a radius and you don't know what the area is. But let's say they say, oh, the radius is 3. What's the surface area? Well, you plug in 3 for the R, and then you could easily find the surface area. The inverse would help you with the vice versa situation, where you do not know the radius, but they give you the surface area, so you plug the surface area in, and then you can easily find the radius. All right, so let me just talk about 24. The number of times a cricket chirps per minute can be found by this function, fine, where F is the temperature in degrees Fahrenheit. Okay, so the number of chirps depends on what temperature it is. So find and interpret the inverse. So you would basically solve for F, and as far as the interpretation goes, it would be such that you could easily find the temperature if you only knew how many chirps there were. Okay, I would replace n of f with an n before you begin that process. Just be n equals 4f minus 160, and then just solve for f. Okay, you don't have to switch anything, just solve for f from that point forward. At least find out what f is in terms of n, we could say. So the interpretation is that if you knew how many chirps there were, you could use that. You could substitute that number in and find out what f equals, what the temperature is. And then they ask, what's the temperature when the cricket's chirping 60 times a minute? Well, you would use the inverse function. All right, I just have to do this. So the inverse function is going to be, first of all, the original function is this. And the inverse function would therefore be n plus 160 over 4. And that's the tool that we're going to use to solve B. What's the temperature when the cricket's chirping 60 times a minute? Well, you would just basically plug 60 in for n, and that would become 220 over 4. So whatever the heck that is, that's going to be F. That's the answer to that one. How many times will the cricket chirp in 1 minute at a temperature of 80 degrees Fahrenheit? So that's them basically maybe baiting you into using this inverse function again, but really the proper function you're going to want to use there is the original function. So the original function is when you don't know how many chirps there are, but you do have the temperature. So you would plug in 80 for that F, and it would be 4 times 80, which is 320. 320 minus 160, whatever that is going to be the answer. Okay. Now they're also trying to throw you off by giving you a 1 there, as though that's some other number we need to take into account. But remember, this is a function that tells you how many times a cricket chirps in 1 minute. So this is just a red herring, okay? Basically, what they're asking here is what does n equal when f is 80? Okay, that's what they're asking. So don't be baited or freaked out by by the introduction of like numbers like that. That was already taken into account up here. Okay, so that hopefully was helpful to my student. For my student at home, please go ahead and watch the video, watch it as many times as need be needed, and apply the principles, practice the problems. I would say even with the video sort of at your disposal as a reference guide, you could always just practice each problem until you get it correctly on your own. Okay, use the answer sheet that your teacher gave you, use the video as much as you need. So good luck to my student at home. The test, I believe, is Friday. So you have a full day to use this video and study with it. And for those of you who are not my student, good luck to you as well. Clearly, this is stuff that is Algebra 2 stuff that you need to know. All right, hopefully it was helpful to you. You know what I'm saying? So I will talk to you later. Take it easy. Bye.